Hello students, Mr. Courtney here, and in this video we're going to be discussing the Bohr model of the atom and also light as both a particle and a wave. So some of the objectives we're going to cover is look at the inadequacies of the Rutherford model of the atom, what was wrong with it, discuss the new proposal put forward by Bohr, and then we're going to describe the relationship between wavelength and frequency of light. So if we look at these two models here, on the left we have the Thompson model or the plum pudding model, where he stated that the atom is a positively charged body with negative particles embedded within it. So again, it's a positively charged body with negatively charged particles embedded within it. And he described it something like a plum pudding, or if you want to say like a chocolate chip cookie, something of that sort. Whereas the Rutherford model stated, that we have a dense positive region and electrons orbiting the nucleus. So these electrons are orbiting the nucleus. Alright, in the Rutherford model, we have the nucleus, which is our dense positive region, and electrons move around it like planets around the sun. And then most of the atom is made up of empty space because this region is so small. The majority of the atom is just made up of empty space. But this model, it did not explain the chemical properties of elements. That is the behavior of the electron or electron behavior, as the chemical properties of an element is determined by the behavior of its electrons. So Niels Bohr had the question, why don't the electrons fall into the nucleus? Now think about it. Electrons are negatively charged, protons are positively charged. So why is it those charges don't attract each other? Why is it the electrons are not attracted to the nucleus? So what he suggested is that yes, they move like planets around the sun, but they do so in specific or fixed circular paths, which he called orbits, or at different levels. And what he was stating here is that if this is our nucleus, we have electrons at different levels. So they are not all the same distance from the nucleus. We find the electrons at different levels from the nucleus. And each level has a fixed amount of energy. So you're in high school. You have 4 levels of high school basically. Freshman, sophomore, junior, and senior. To move from a freshman to a sophomore, you need to have a certain number of credits. Then to go from sophomore to junior, you need to have a certain number of credits. So it doesn't matter if you've been in high school for 3 years and if you don't have enough credits to be classified as a junior, you will still be a freshman, hopefully not, or a sophomore, hopefully not, but maybe. It just depends on the number of credits you have. So it all depends on the amount of energy. So each level or each orbit or each energy level requires a certain amount of energy. So in the Bohr model, he suggested again that electrons orbit the nucleus much like the planets orbit the sun. However, electrons are found in specific circular paths around the nucleus, and they can jump. So they can jump from one energy level to another. In other words, they can move from one energy level to another. Okay, so let's take a look and see what he meant by this. Now let's see. Picture this. This is our nucleus, positively charged region. Then we have our energy levels around it. So I'm just going to draw these, not perfect circular, but circular enough. These are our energy levels. So what he's saying, if we have an electron in this energy level, it can jump from this energy level to this energy level. And then if you have one that's in this energy, in the second energy level, it can also jump to the third energy level. So they can change energy levels, but at some point they have to come back to their original energy level, and we'll talk about that in a while. So that's basically what he's talking about, that these electrons can absorb energy, they can gain energy and jump to another energy level. So think of energy levels as the rungs of a ladder. So we have a ladder. I'm going to attempt to draw a ladder for you guys, so don't laugh at my horrible drawings, but hopefully this helps you guys. So think of the rungs of the ladder. So the rungs of the ladder are things that you would stand on if you were climbing the ladder. Now, you cannot stand in between these two rungs. There's nowhere for you to put your foot here to stand on it. So you could either be on one rung or the other, not in between. The same things. Electrons cannot exist between energy levels. So they either have to be in one energy level or in another. Now there's a popular song from the Caribbean that says either you're in or either you're out. Or as we would say, either you're in or either you're out. Who you rolling with? Okay? So either you're in one energy level or the other. You can't be between. Now a quantum. Think of a quantum. So a quantum, what does that sound like to you? What word does that remind you of? If you said quantity, yes, you're correct. Quantum meaning an amount of energy required to move an electron from one energy level to another. So how much energy is required to take an electron from this energy level to this energy level, or let's say from this energy level all the way to this one? So that is what quantum means. Now there was one problem with the Bohr model, where he stated that electrons travel in fixed orbits. It later became known that electrons do not travel in fixed orbit. Instead, they're found in a region, what we call an electron cloud. Okay? So this model now became known as the quantum mechanical model, or the electron cloud model. And a simple analysis of this is, think of it in this way. Alright, so you have a box, or I like soccer, you have a goal. Now when someone shoots the ball at the goal, in other words, for the goal to be scored, the ball can pass anywhere in between here. But doesn't mean it will always be found in the same place. So it's the same thing with the electrons. As the electrons orbit the nucleus, they do not do so necessarily in a circular path all the time. So they can go like this. Just assuming, not necessarily. Or they can go like this. But they're still orbiting the nucleus. It's not fixed. The orbit is not fixed. But why? So if this is true, why is it we still study or use the Bohr model? It's just that the Bohr model makes it easier to understand the concept of energy levels. That electrons are found in different orbits. Even though it's not fixed, but they're still found in different orbits. And this model, the Bohr model, makes it easier for us to understand the concept of energy levels. And as we stated before, the electron cloud is an area where there's a chance of finding an electron. So there's a chance of finding electrons anywhere within this electron cloud. Now, does it mean we will actually find an electron cloud if we look exactly at these points at any point in time? Not necessarily. We may get lucky, we may not, but it's just there's a chance. Just as you have a chance of winning the Powerball lottery. Doesn't mean you will win it, but you still have a chance. Now we talked about the atoms absorbing energy. As an atom absorbs energy, remember, if it absorbs energy, it takes that energy in. So the electrons now absorb that energy and they change energy level. So they move to a higher energy level. We term these electrons as being excited. Think of you, or think of a child eating lots of candy. As you eat more candy or more sugar, they get more hyper. They get more excited. They tend to bounce around. They tend to be more erratic in some cases. So they're excited. They've jumped from one energy level to a higher energy level. Now, as time goes on, they lose that excitement. The energy wears off. So they have to release that energy. So they have to go down. They have to go back to their normal energy level or their ground state. When they do so, the energy is released in the form of light. And that makes them glow. So whether you have something that glows in the dark, as one student said, it's a bird. Whatever it is, it glows in the dark. Or if we're looking at light, you're looking at your cell phones, you're looking at fireworks. All these things are related to atoms absorbing energy and electrons moving to a higher energy level, becoming excited, and then losing that energy, releasing the energy in the form of light when they go back to their ground state or their normal energy level. That causes them to glow. Now, an understanding of the modern view of the atom requires some knowledge of the nature of light. Light is thought of as being waves moving through space. Now, there are several terms and symbols that we need to be familiar with as we come and to describe a wave. The first term we need to be familiar with is the wavelength. So this is what we refer to as the wavelength. The distance between peaks, so from one peak to another, or the distance between two identical points on neighboring waves. So if I look at this point, the next identical point is here. So that would be the same as a wavelength. Or if I look at this point to this point, that is still a wavelength. So from here to here, here to here, here to here. All these measure a wavelength. Now the origin is a normal resting position of the wave. So now the amplitude is the maximum distance the wave is displaced. So the highest point or the greatest distance the wave moves away from its resting position. Now the crest is the high point of the wave, the peak, and the trough is the low point of the wave. So if we look at the first statement here, which states electromagnetic radiation propagates through space as a wave moving at the speed of light. We've talked about radiation as a transfer of heat when objects are not in contact, or a transfer of heat in the absence of matter. So we know that. Now think of propagates. What does that mean? You may have never seen this word before. But if we look at the context in which the word is used, electromagnetic radiation propagates through space as a wave moving at the speed of light. So if we think of propagates, think of movement. So it moves, it travels through space as a wave moving at the speed of light. So let's look at this here. We have two sample waves. We have the amplitude of one, the first wave. We have the wavelength shown at different points. We take from crest to crest or from trough to trough. The wavelength will be the same. Now we look at another wave in the same period of time. We look at the wavelength. We'll talk about that symbol here and the wavelength. So we have low frequency and high frequency. Now, how is wavelength frequency related to the speed of light? The speed of light, c, which is a constant, meaning its value does not change. It's actually 2.99 something, but we round it off to 3. So it's 3.00 times 10 to the 8 meters per second is equal to lambda. It looks like an upside down y. It's actually Greek letter. Lambda, which is the wavelength. So lambda is equal to the wavelength, and it's measured in meters. Now, this here looks like a V. It is not a V. It is pronounced nu. N-U. N-U, nu. You need to know this. This is the frequency, and the frequency is measured in units of hertz, or seconds to the minus 1. Now let me clarify something on seconds to the minus 1. Seconds to the minus 1 means 1 over seconds. Okay, so when we say 1 over second, or second to the minus 1, or it also means per second divided by seconds. So that's what that unit means. Alright, so keep this in mind. C is equal to lambda nu. The speed of light is equal to the wavelength of the wave times its frequency. Now let's go back to this picture here. We have 1, 2, 3, 4 waves. And in the same period of time on the second one, we have 1, 2, 3, 4, 5, 6, 7, 8. So here we have 4 waves, and here we have 8. So we have 4 frequencies, a frequency of 4 and a frequency of 8. So when we talk about the frequency, we talk about the number of waves that go by each second, or the number of cycles. A complete wave is called a cycle. Okay, or cycles per second gives us the unit of frequency, or is also known as the hertz, as we said before. So now we're going to look at the relationship between wavelength, frequency, and energy. So in the first wave we have 4 cycles, which is 4 hertz. Second wave we have 8 cycles, which is 8 hertz. And in the third wave we have 16 cycles, which is 16 hertz. So we have our wavelength. Here in the first one, lambda 1, we have a long wavelength. Long wavelength, low frequency, because we only have 4 cycles. Low energy. As we go to the last one, we have a very short wavelength. Look at the distance between the crest and the crest, or the trough and the trough. They're significantly smaller than the first one. So we've shortened the wavelength. We've increased the frequency, because in the same period of time, we have more waves. We had 4, we went to 8, and now we have 16. So we increase the frequency. If we increase frequency, we also going to increase energy. So what does this mean? This tells us that there is a direct relationship between frequency and energy. Direct means what? What it's saying, if I increase frequency, I increase energy. Okay, here again. Increase frequency, increase energy. If I decrease the frequency, I'm going to decrease the energy. That's essentially what it means. Now look at the wavelength. Okay, so let's do it in terms of wavelength now. So we have decreased wavelength. We increase frequency, and we increase energy. So they're inversely related because they go in the opposite direction. If I increase the wavelength, we're decreasing frequency, and we're also decreasing energy. So these are also inversely related. Now, since they're inversely related, let's look at this relationship. Let's apply some math to it. Yes, I know. It's chemistry. Okay, so take a deep breath. Please, why do we have to know the math? Knowing the math will help you to understand this a lot better. So look what we've done here. We went from 4 to 8. So we've multiplied by 2. And from 8 to 16, we've multiplied by 2. So if we've gone from here to here, we've multiplied by 4 in terms of the number of cycles. The wavelength is going to be halved. So we're going to decrease the wavelength by 2 times up 2 divided by 2, every time. Since we multiply by 2 and wavelength and frequency are inversely related, if we multiply wavelength by the frequency by 2, we have to divide the wavelength by 2. And if we go from the first wave to the third wave, since when we multiply by 4 our frequency, that means our wavelength will now be divided by 4. Okay, so let me write this: nu times 4, lambda would be divided by 4. Alright, so light also has energy. So the energy of the electromagnetic wave or electromagnetic radiation is directly proportional to the frequency of the radiation. So E, our energy, is equal to h nu. E is the energy in joules or kilogram meters squared per second squared, or we just simply use joules, is equal to Planck's constant, which is this means the value does not change. It's going to remain the same every time. 6.626 by 10 to the negative 34 joules second, or joules times second. And nu, which we discussed already, is the frequency in hertz, or per cycle per second. So light is thought of as a particle because it comes in chunks, or as a wave because we can measure its wavelength. Now, by combining these equations, E is equal to mc squared, C is equal to lambda nu, E is equal to half mv squared, E is equal to h nu, we can end up with this equation: lambda is equal to h divided by mv. So now we've gone from we're using m, and we're using v, not nu. So h, Planck's constant again, m, our mass, and v is velocity. So from Louis de Broglie, and that is called de Broglie's equation because it helps us to calculate the wavelength of a particle. This is for wave. This equation is for a particle. So if you're given the mass and velocity of a particle, you can calculate its wavelength. Or if you're given the wavelength and the mass, you can calculate its velocity. Or if you're given wavelength and velocity, you can calculate the mass of a particle, whichever way you want to do it. So it's used to calculate wavelength of a particle mainly. So is light a particle or it's a wave? We have the theory. There is the wave-particle duality of light, as shown by J.J. Thompson. Remember him? And his son George Thompson. They both won a Nobel Prize for describing. One described electron as a particle, so that was Thompson. J.J. Thompson, that is. And his son George Thompson, he said electron is an energy wave. So they were both correct because light can behave both as a wave or as a particle, or it can exist as a wave and as a particle. But it cannot be a wave and a particle at the same time. So it's either or. Okay, so here is a sanity break. Physicist Sir Arthur Eddington once said, "No familiar conceptions can be woven around the electron. Something unknown is doing we don't know what." Again, something unknown is doing we don't know what. Okay, so light can have a variety of frequencies, as we can see here. Also different varieties of wavelength, as we can also see here. Now the range of frequencies and wavelength is divided into bands. We take all these together, it makes up what we call the electromagnetic spectrum. So if we start at one end, we go from radio waves to radar, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Is it interesting to note as we go in this direction, wavelength, our wavelength will decrease, so it goes down. As we go in the same direction, we go from radio waves to gamma rays, what happens to our frequency? Our frequency increases. That also means our energy follows the same as frequency. So our radio waves will have the longest wavelength, what happens to the frequency? They're going to have a low frequency, and they're going to have a low energy. But as you move from radio waves across to gamma rays, frequency is going to increase, energy is also going to increase, but our wavelength is going to decrease. Now in between infrared and ultraviolet, we have the visible light spectrum. And these are the colors here that make up white light. All these colors put together make up white light. If you take white light, pass it through a prism, it will give you these colors, or as you see in the colors of the rainbow, as you would say. So we have red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. Roy G. Biv. Still remember the first day I learned this from one of my first physics teacher, Mr. Pandey. That was, yeah, let's just put it was a long time ago. But I still remember it. Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. The colors of the visible spectrum. Notice red has the lowest energy because it has the longest wavelength of 700 nanometers. That N means nano. Violet has high energy at 318 nanometers. So what does this mean? Nano, okay, N-A-N-O, or N, means times 10 to the negative 9. So 700 nanometers would mean 700 times 10 to the negative 9 meters. In other words, 1 meter is equal to 10 to the 9 nanometers. This will come in very handy. So it's important that you know this and you pay attention to it. 1 meter is equal to 10 to the 9 nanometers. Or nanometer, or nano means times 10 to the negative 9. Alright, so let's look at some examples. So in the first example, we're asked, what is the frequency of a photon of light? Now a photon also refers to a quantum or a packet of light. So what is the frequency of a photon of light that has a wavelength of 5.78 times 10 to the negative 7 meters? So look at what we're given. We're given wavelength, which is lambda, and we want to find the frequency. So we think about the equations we just looked at. Which equation connects frequency and wavelength? C is equal to lambda nu. We know C is a constant, that's the speed of light. We're given the value for lambda, or the wavelength. The only thing we don't know is nu. So if we divide the speed of light by our wavelength, we get nu. And since we started with 1, 2, 3 significant figures, our answer must be given to 3 significant figures. Notice the units of hertz, or we could have used seconds to the minus 1. Okay, either of these would work, or cycles per second. In the second problem, we're given frequency and asked for wavelength. We use the same equation because that connects frequency and wavelength, or wavelength and frequency. We know what the speed of light is. We know what the frequency is. And if you wanted to put, we could put per seconds. It doesn't make a difference. To solve for lambda, we divide the speed of light by the frequency. And we started with 2 significant figures. We need to end with 2. 4.4 times 10 to the negative 7 meters. Alright, in our third example, it says the electron in the diagram is dropped from its excited state to its ground state. In the process, it emits a photon with a frequency of 6.65 by 10 to the negative 10 to the 14 hertz, sorry. So 6.65 by 10 to the 14 hertz. How much energy is in the photon of light? So here we want to calculate energy given frequency. So we go back to our equation. E, or the energy of the photon, is equal to h, which is Planck's constant, times nu. So we know Planck's constant is this 6.626 times 10 to the negative 34 joules second. And we multiply by the frequency in hertz, which is 6.65 times 10 to the 14 hertz. This is the value we get. We started with 3 significant figures. So this is our answer, 4.41 times 10 to the negative 19. Now, what you should do at this point, and I should have said this earlier as we work these examples, I know I've shown you exactly what you need to do, but it is important for you to stop and work the problems. Ensure that you get the same answer I'm getting. So you can pause the video or go back and work them. Just make sure that you're getting the same values that I'm getting as we work along. That way you know for sure you're doing it correctly. Okay? In this question, we have to do something a bit different. It says a photon of light with a wavelength of 5.28 times 10 to the negative 7 meters is emitted from an atom as an electron travels from its excited state to its ground state. How much energy difference was there between the excited state and the ground state of the electron, assuming all of the energy is contained in a photon of light? So we're given wavelength, we want to find energy. So there are certain equations we need to look at. We know C is equal to lambda nu. More like a V, sorry. So let me write this over. C is equal to lambda. That may not look exactly as it should be. So we also know E is equal to H nu. Not too bad, but I guess that will work. So nu is equal to C divided by lambda. Now, take this as being a dollar bill. this as being 4/4. Can I replace the dollar bill with 4/4, or use the 4/4 to replace the dollar bill? They're the same. Think about it. All right, good. So let's do that. So now E will be equal to hc over lambda, which is this equation here. So Planck's constant times the speed of light is equal to our divided by wavelength can give us energy, and we're not going to pay attention to this part because we don't use F for frequency. So again, we use this equation. We know what Planck's constant is. We know what speed of light is. This is our two constants. So the only thing we need to be given is the wavelength to find our energy, which works out to be 3.76 times 10 to the negative 19 joules, because energy is measured in joules. Alright, so that takes us to the end. We talked about the Bohr model, where he suggested that electrons orbit the nucleus in fixed energy levels, or in fixed orbits, and we understood now that this is not the case. Instead, the electrons are found in certain regions, or what is called an electron cloud, which we'll discuss in more detail. We talked about the wave-particle duality of light, that light can exist as both as a wave and a particle. We talked about the electromagnetic spectrum, the parts of the wave, the relationship between frequency and energy and wavelength. We talked about the parts of the wave and using these equations to calculate different things. So if we're given energy, we want to find wavelength, we know what we need to use. Now, one of the things you need to pay attention to when you're doing these problems, pay attention to what you're given. Look at the equations you have and see which quantities you're given and which equation best suits which quantities you're given and what you want to find. So that will help you a lot when it comes to solving these problems. So again, hopefully this was very helpful to you guys, especially if you missed class, so you don't have to worry about coming and ask me, oh, what we did in class. So there you have it. Take your time, go through it. You can go over it as many times as you want. All right. So until the next time, guys, bless. I'm gone.